So for this map diagram, the function f has the ordered pairs a1, b1, a2, b2, a3, b3, and a4, b3. And so to recognize that this is a surjective function, it must first be true that it's a function, and so each of the elements in the domain A must appear exactly once as the first coordinate in the ordered pairs. And to have a surjection, each of the elements in the codomain B must appear as elements as the second coordinate in the ordered pairs at least once. And that is true, where in this case the element B3 appears twice. And again, to emphasize notation, to say that the ordered pair A1, B1 is in the function f is the same as to say that f of A1 is equal to B1. And for example, f of A2 is B2, f of A3 is the same as f of A4, which is B3. Okay, so new definition. A function f mapping A into B is an injection or injective function if no two distinct elements in the domain are paired with the same element in the codomain. That is, the function f from A into B is injective if and only if for every pair of elements A1 and A2 in the domain A, if f of A1 is the same as f of A2, then A1 and A2 must be the same element. So let's look at a map diagram. So for a function to be injective, no two elements in the domain can be mapped onto a common element in the codomain. But an injection does not have to be a surjection, and so it is not necessary that each of the elements in the codomain is mapped onto. So let's look at the ordered pairs for this function. Based on this diagram, the ordered pairs are A1, B1, A2, B3, and A3, B4. So again, in order to have a function, each of the elements in the domain must appear exactly once as the first coordinate in the ordered pairs. And to be an injection, no two distinct first coordinates can have the same element as the second coordinate. And again, in terms of notation, the ordered pair A1, B1 is in the function if or is denoted f of a1 is equal to b1, and we have f of a2 is equal to b3, and f of a3 is equal to b4. Okay, so new definition. A function f from a into b is a bijection or bijective function if it is both surjective and injective. So a bijection is a well-behaved function. Let's look at a map diagram. So for a function to be a bijection, it must be a surjection, and so each element in the codomain must be mapped onto by an element in the domain. And each of the elements, each distinct element in the domain can be mapped to a distinct element in the codomain. No two can be mapped onto the same element. And so for a bijective function, there is a one-to-one correspondence between the elements in the domain and the elements in the codomain. So for this diagram, we have the function f contains the order pairs a1, b1, a2, b2, a2, b3, and a3, b2. And we have f of a1 is equal to b1, f of a2 is b3, and f of a3 is b2. So let's look at an example. The set, which we denote z sub 5, which contains the elements 0, 1, 2, 3, and 4. So 5 elements from 0 to 4. This set is the set of integers modulo 5. Now, when we do modular arithmetic, modulo 5, then any multiple of 5 is the same as 0. So let the function f from the set of integers modulo 5 into itself be defined by f of a is a squared. Let's determine whether this function is injective or surjective. So let's calculate the squares of the elements in the set. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared, which we need to express as a multiple of 5 plus a remainder, or plus a smaller number. We have 5 times 1 plus 4, and so this is 4. And 4 squared is 5 times 3 plus 1, which is 1. And so note that the range of the function f is the set containing the numbers 0, 1, and 4. And so the function f from the set of integers modulo 5 into itself is not surjective, since the range of the function f is not the entire codomain, or alternatively, as a counterexample, there does not exist an element a in the set of integers modulo 5 such that a squared is equal to 2. And so it is not true that for every element in the codomain, there exists an element in the domain such that the element in the domain maps onto that element in the codomain. Further, this function is not injective, since, for example, f of 2 is the same as f of 3, that is, 2 and 3 are mapped onto the same number, which is 4, but 2 is not equal to 3. So as an exercise, let f be a function from the integers modulo 5 into itself, and let that function be defined by f of a is 2 times a plus 1. Determine whether this function is surjective or injective. So in general, let's consider how we would go about proving that a function f from a into b is surjective. So we could use the definition and we could prove that for every element b in the codomain b, there exists an element a in the domain a such that b is equal to f of a. That is, there is an element in the domain that is mapped onto the element b for every element b in the codomain b. We could also prove that the range of the function is the entire codomain b. So now let's consider how we would go about proving that a function f from a into b is injective. Again, we could use the definition, and so we could prove that for every pair of elements a1 and a2 in the domain a, if f of a1 is the same as f of a2, then it must be true that a1 and a2 are the same element. Now this is an implication, and so we could prove it indirectly by proving the contrapositive, and so we can prove that for every pair of elements a1 and a2 in the domain, if a1 is not equal to a2, then f of a1 is not equal to f of a2. Okay, so now let's consider a very familiar term. Let R be a relation. The graph of R is the set of ordered pairs which we'll call xy in the relation represented as points in a Cartesian coordinate system. So a graph of a relation is a visual representation of the ordered pairs as points in a coordinate system, a Cartesian coordinate system. So when we have a graph of a relation, there are some useful line tests that will tell us some information about uh, the relation and in particular functions. So let's consider some useful line tests. So first, a vertical line intersects the graph of a function at most once. A horizontal line intersects the graph of an injection at most once. A horizontal line intersects the graph of a surjection at least once. And a horizontal line intersects the graph of a bijection exactly once. Okay, so we will end here for now. Next time, we will consider some additional concepts related to relations and functions, and then we will begin to construct subsets of the real numbers.